Hello friends. So in this lecture I am taking one tutorial on Python program application to calculate the natural frequency of multi-degree freedom of system. So here I have one problem from one of the book where it is a 2-degree freedom of system. It is a having two masses. One is with mass m, second mass with 2m, and these are connected by such as three springs. All of are having stiffness of k. So let's see how can we utilize Python code to calculate the natural frequency of these 2-degree of freedom system, and we will compare with analytical calculation as well. So let's start. I have created one Python file in Sublime Text Editor. You can use any as per your convenient. I need to import certain libraries for calculation. So first I am importing NumPy as np, then I am importing SciPy. From that I need linear algebra, so scipy.lin alg, and from that I will import from here I have to use from scipy import eig, that is eigen calculation. So first I will define mass m, let's say 15 kg is my mass, and k is 100 for sample. So I have to define matrices. So I am not going into equation part, so I will directly define the matrix for this. So if you study some vibration part or how to get to these matrices, you can refer some books. So first m, that is mass matrix, np dot array. I am utilizing array function from NumPy. So syntax I have to follow normal bracket then square bracket. So since this is a 2 by 2 degree of freedom system, so mass matrix is 2 by 2. So first row, then comma, let I will create second row. So this is first row. I need to fill the mass matrix. So there is convention that mass matrix is a diagonal matrix with diagonal elements are equal to mass of the system. So first mass is m1, that is m. Non-diagonal elements are 0 normally for mass matrix, so 0, and second mass is the 2m. So this is mass matrix. We are ready for verification. We will print this, print m, and run it with control B. So 15 0 0 30. So this is my mass matrix. Okay, similarly the stiffness matrix should be there. So stiffness matrix can be calculated by different way. So it would be the 2 by 2 matrix. So let's first define np dot array. It is 2 by 2 matrix. So first square bracket, then first row comma second row. So first element, that is k11. So k11 means what is the stiffness of the spring which are connected to mass 1. So k11, so there are two springs k and k, so total would be the 2k. Or if there are different stiffnesses, so you can put k1 plus k2, and the k12 element, so this is a k11 element. So for just I will write initially K11, K12, then K21 and K22. So we need to fill these elements. So I will put in second row so that it will be easy for understanding. So K11 we got the stiffness of the spring which are connected to mass 1. So those are K1 plus K2, that is 2 into K. Sorry. Then K12, that means what is the stiffness of the spring which is connected to mass 1 as well as mass 2. So what is the stiffness of the spring? There is only one spring between mass and mass 1, mass 2, that is this middle spring, and it will come up with negative sign. Non-diagonal elements would be the negative. So same here, K21 means the spring which is connected to mass 2 and 1, again it would be the same. K22, the spring which is connected to mass 2 only. So here this spring and this spring, there are two springs, K2 plus K3, it is nothing but 2 into K. So our stiffness matrix is ready. We will print K as well. Print K, Control B to run the Python file. 200 minus 100 minus 100, 200. So okay, we are ready to go. So next part we will calculate the eigenvalues and eigenvectors. Eigenvalues are nothing but the natural frequency of the system. So eigenvalues. So there is syntax. So we will use I e values. So we'll create one variable e values, that is eigenvalues, and e vectors. So for that we will call this eig function from the SciPy library which we have imported at the top. So we have to define the stiffness matrix first, then mass matrix. Let's run it whether we are getting any error. So we are not getting any error, so we are good to go. And then the natural frequencies is equal to, if we take square root of eigenvalues, then we'll get the natural frequencies. So np dot square root of, so sometimes eigenvalues can be the complex function as well, so we have to take only real part of the complex number. So again we will use np dot real to get only real part of the eigenvalue. So e values, this one. Okay, so we got, and now we can print natural frequencies, print natural frequencies and control B. So we got 3.97, 2.01. So sequence can be anything like so let's say np dot sort natural frequency. So a smaller frequency I will print first and then second one. So what is the analytical solution for this? So first is, let's say, where is book? So for this problem, same problem, so omega 1 is square root of 0.364. Let me take to the Excel sheet. We will calculate. So here, so our K is 100, M is 15. So omega 1, let's say, is equal to square root of 0.634 into K divided by M. So 2.05 omega 2 is equal to 2.366. So square root of 2.366 into k divided by m. So analytical calculation is 2.055 3.97, and our code is same solution we are getting. So this method we can utilize to calculate the natural frequencies of the system. Only thing that we need to get correct mass matrix and correct stiffness matrix. So there is a ready-made function eig from SciPy library we can utilize for that. Thank you for watching.